Well, disaster struck. I have done a total of 4 smelts now. 3 of them I have recorded and put on the channel here. The 4th one, because the 3rd one went so well, I thought I'd just go ahead and do a quick one. And I melted off about 1/3 of a pound of lead off that piece of iron from last time and set it aside, but a lot of the lead was bound up kind of in a mixed up chunky flux because it was so thick. So I decided to just put that whole thing in the 4th smelt, let it melt down to the bottom and separate out that way, which is a pretty reasonable idea. But I also, instead of putting in any borax, I went with all soda ash. Now, soda ash, as we discussed previously, when it decomposes, it releases CO2. Without the borax to maybe help thin it up a little bit, I ended up with a little thicker flux, and when it boiled, the individual bubbles couldn't pop or resisted popping. So the material foamed up and it overflowed out of the crucible. And when it did that, you can kind of see the bottom of the lid here is not in great shape. It's got stuff plastered all over. This would technically still work. I'm not happy about this, but this isn't a disaster. The disaster is where it ate this entire section of KO wool away, and stuff down here at the bottom. Down at the bottom, and kind of messed up the fire brick a little bit, but mostly just ate the KO wool. This is not usable anymore. Now I can fix this. I have to clear all the KO wool out and replace it, which is doable, and I intend to do that, but for right now that's not the major problem I'm having. This is the slag from that melt, and we'll go over here a second, but what you're going to find as we go through this, I don't know if you can see, let me see if I can get my camera angle right, how sparkly that is. There's a lot of metal left in that. This piece is actually the lead prill off the bottom. And once again, I'm having a problem seeing my camera. Okay. There's the lead prill off the bottom, but if you flip it over and look, it's just got all this junk on it. There's still some quartz. There's definitely a sulfide layer left because the reaction hadn't completed. In the individual pieces, I just kind of pick through and find one, you'll see every so often just these pockets of metals. There's a little quartz here, a little pocket of just like lead powder, and like there's a little lead what would you call it, just a little lead bead there that broke in half. So there's a lot of my metal is in this, 2 smelts worth. The problem is I only have a limited amount of material, and I can't afford to just throw this away and start over. There's just not enough metal left. So what I've decided to do is to try to reprocess this. Now obviously the easiest way would be to just throw it back in a repaired furnace and melt it down again. But seeing as how I'm having problems with the flux being so thick, partially because of the amount of quartz possibly, I'm not sure, I want to try to separate the slag from the usable materials, either the sulfide layer that's left or any metals that are left. So to do that, I need to remove the slag as cleanly as possible. Now I have one shining benefit here, because this had almost no, well, had absolutely no borax in it. When you have this basic slag and you leave it out in the air, it tends to become crumbly because it absorbs moisture. And I will go over the complete chemical reaction of this a little bit in just a moment. I'm going to jump to the whiteboard here in a second and go over this. But basically, I believe, done correctly, I can break this down with water. To do that, I'm going to heat the water to make the reaction happen faster. And I'm also going to have to break this stuff up, just to give the water more access, more surface area. I will probably start with just that lead prill and try to remove what's on it, or as much as I can, and then do the rest of the material in a second go, just to make that first one go a little faster. Because that is where the majority of my material is, and I'd like to recover it. So, with that said, I'm going to jump over to the blackboard, or the whiteboard, and explain chemically what I'm about to do. And then I'll jump back here and we'll do it. Alrighty, let me get this set up. Okay, let's see if I can make this just as wildly confusing as possible. So what we're talking about here is in the chemistry of the smelt. At this point, we're only looking at the flux. Okay, we're not dealing with anything to do with the galena, the sulfides, the metals, nothing. We only have two things that we're going to worry about. One of those is the flux that we're using, and that is the soda ash. Soda ash, and that is Na sodium 2CO3. That's the chemical designation for it. The other thing that we're kind of interested in is going to be the quartz, which is a silicon dioxide. So that is silicon O2 dioxide, and that is the quartz, or the silica, or the white sand, or however you prefer to say that. Now the soda ash, when we heat it up to a certain temperature, actually breaks down, and we've covered this before, but it's always good to review. The NaCO3 becomes sodium oxide, and that is Na2. Oh, I've got that wrong. I am going to mess that up, aren't I? I believe that becomes 2. I'm going to have to go back and figure that, but regardless, it becomes sodium oxide. Now, if you take the sodium oxide and the silicon oxide in the flux, those two will bind to each other quite aggressively. The sodium oxide will actually eat glass if you're not careful. It also does a number on ceramic crucibles. But what that will give you, when these two combine, is a third product. And that third product is Na, which is sodium, 2 silicon O3. And that is technically referred to as sodium silicate. So that is sodium silicate. And keep in mind, all we're dealing with is these two chemicals. We're ignoring the galena, we're ignoring the sulfates, we're ignoring the iron, pyrites, everything. So when these two are mixed in that ratio, they form this, and it's like a kind of a glass. It's liquid because it's glowing hot. But if you let this cool down, it becomes a solid. And if you take that solid and you add water, okay, this becomes sodium silicate hydrate. Okay, so then this is going to become hydrate plus H2O with water. Okay. Now the interesting thing is sodium silicate hydrate is also known commercially as water glass. Another name for it when you're dealing with furnaces and smelting is rigidizer. This is the exact same stuff that you buy to spray on your kale wool to prevent the fibers from flying around and going into your lungs, which is actually, this is an important safety thing. The interesting thing about water glass or rigidizer is it's water soluble. Okay, so if we take this sodium silicate, dump it in a bunch of water, we should be able to basically dissolve the sodium silicate into water. And the implications for that, and the reason I brought this all up, is that I have a failed smelt of mixed materials, metals that won't dissolve. I've got some sulfides that are not going to dissolve, and I've just got a ton of slag in all the worst possible places. So I'm going to try and put my sodium silicate that I have produced as my slag into water and hopefully dissolve it and leave the undissolvable things behind. Now, this does not account for things like I've got iron oxides in there that have been absorbed into that flux. So I'm not 100% sure how this is going to go. And if I just use the soda ash and the quartz, I could make water glass, or rigidizer if you prefer. I can actually use that on my kaolin. But in this case, I'm just coming at it as it's a solid form of water glass with a bunch of impurities in it, and I want the impurities. I do not want the water glass. I'm going to try and superhydrate this stuff into a liquid by boiling it in water and then pouring it off and leaving behind the materials I do want. So that's the plan.